right, today we are going to look at graphing trigonometric functions. We have already started this a bit with our fettuccine activity, but this is just a follow-up to create these nice organizers. So we're going to start by filling out this table for sine's value at assorted angles. So go ahead, pause the video, and fill out the table on your own. You may have noticed that the values, as you go on, there's less and less values, mostly out of convenience of time, but also because those radical ones are going to be really messy. Now we're going to graph these. So at 0, go ahead and make a graph, and pause the video, make a graph, and then we'll come back together. All graphed? All right, so now I'll have 1, and then 0.86, 0.77, 0.5, and 1. So, and these aren't perfect, about 0.8, 6, 0.7. So then these are a little more precise. This is just a straight mark. So you have something kind of like that to there. That's one cycle. We know because of all the coterminal angles that it's going to keep repeating. So this will be back up at 1. And then here you got -1. And this repeats as well. Notice I'm not putting arrows at the end because arrows would tell me that the graph is going down towards negative infinity or up towards positive infinity instead of this oscillating that's happening. Now, let's fill in some of this other stuff. Our domain will be all real numbers. Our range will be -1 to 1. We knew that already from an earlier lesson, but we can see it visually now in that graph. That we keep on going over and over and over again, and that the lowest is -1 and the highest is +1. Our period length, as a reminder, period length is how long it takes before the graph repeats itself. In this problem, our graph starts repeating itself at 2 pi. And that comes from our coterminal angles again. Amplitude. Amplitude is a new vocab word here, and that's talking about how high the hills are in comparison to how low the valleys are from the middle of the graph. So my middle of my graph is right here, and my hills are 1 unit above, and my valleys are 1 unit below. So my amplitude here is 1. Now, we also have some critical points. Our critical points are basically going to be all the values in that table that gave us nice answers. And I'm saying nice in quotations. You just can't see it. It's the kind of answers you like to get instead of all those fractionals and irrational answers. So you can write this as a table like I am, or you can write it as a list of coordinate points. We will say 0, pi over 2, pi, a little more space, 3 pi over 2, and 2 pi. And then at 0, it's 0. At pi over 2, it's 1. At pi, it's 0. 3 pi over 2 is -1, and 2 pi is 0 as well. So this is just our unit circle quadrantal angles, and quadrantal means it's the angles that divide into the quadrants, and the evaluation at it, which comes out as integer values. These are what we're going to do our transformations on. Now, take a look at the graph. And I know you're not going to be able to answer me this, but does this graph have symmetry over the y-axis? Does this graph have symmetry over the x-axis? Or does it have symmetry over the origin? Take a moment to answer that question to yourself. This graph has symmetry over the origin. That means if I rotated it 180 degrees, it would look identical. So this origin symmetry that we have here tells me that it is an odd function, which we knew. We knew that property already, but now we're confirming it from the graph. Go ahead and flip the page over and take a look at cosine curves. I would like you to do the exact same thing. So you're going to pause the video here, you're going to fill out the table, and create the graph. For real life, pause it. Okay. All right, so you should have something that looks sort of like this. Notice here that we have nice curves. It's not jagged or not like Charlie Brown's shirt. It's just nice continuous curves. Here, our domain, just like sine, was all real numbers. Our range, just like sine, is -1 to 1. You can see that visual that where the lowest is at -1 and the highest is at +1. Our period length, just like sine, is 2 pi. And our amplitude is 1, just like sine. Our critical numbers here, apologize. Our critical numbers change a little bit. Numbers. Or critical points, you could call it either way. X and cosine x. We're still going to use our quadrantal angles here, but because it's a different function, it's going to look slightly different. So we're going to be 1, 0, -1, 0. And as a reminder, we're getting these values by looking at these different angles on the unit circle. So on those different angles on the unit circle, what is the x value? Now, as I look at my graph, I'm going to ask the same question. Do I have symmetry over the y-axis, over the x-axis, or over the origin? I have symmetry here over the y-axis. Since I have that y-axis symmetry, we can call this an even function, which we knew already. We knew that property from our properties of trig functions, but here I'm now confirming that property with our visual of the graph. So what I'd like you to do is pause the video and graph both sine and cosine on the same axes. And then we're going to ask, how are they similar and how are they different? It's a good idea to also graph them in 2 different colors. You can use a whiteboard, you can use paper, whatever you'd like. You should get something like this. Here I have sine as my green graph and cosine as my blue graph. And these are both what are called sinusoidal graphs. Sinusoidal graphs have these hills and valleys and things like that. Next thing I want to look at is y equals 3 sine x. Now this 3 is going to have an effect on it. Ask yourself, do you think that 3 is going to be a reflection, a stretch or shrink, or a translation? Hopefully, you said that should be a stretch or shrink. But my follow-up question is, do you think it's going to affect things vertically or horizontally? If you're not sure, go back to your transformation notes. We did transformation of functions way back at the beginning of the year, and those rules of how the placement affects what it does, whether it's affecting vertically or horizontally, still are true in trig functions, as well as all of the polynomials, square roots, absolute values, and all those other functions we studied earlier, and piecewise functions as well. So, hopefully you have noticed by now that is going to affect it's a vertical stretch. Okay, so this is a vertical stretch. That means instead of my hills and valleys each being only 1 unit above and below, my hills and valleys are now going to be 3 units above and 3 units below. I can model this by doing our transformation of functions by multiplying the y values by 3 in that table, but I'm going to kind of just do it visually on the graph. Pi over 2. I'm doing every other box here because I want to keep my graph kind of tidy. And then 1, 2, 3. And then boom, 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 1, 2, 3. And there. So I get a graph that kind of looks like this. Again, notice this is 1 cycle. I can see my pattern that I'm going over 2 and up 3. So I can keep going over 2, up 3, over 2, down 3, boop, 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 boop. And then I can continue it this way as well. 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3, 1, 2, 3. And some more over here. Just another reminder, and I know I've said it before, and I'll say it again. we do not put arrows on the end of this graph. And the reason we don't put arrows on the end of this graph is because it is not continuing down towards negative infinity and positive infinity. And that's what an arrow would be telling me. Because this graph is oscillating, which it means it's going from -1 to 1 back and forth over and over and over again, we either have our graph just stop or we go all the way to the edges. So what I have here is that 3 is also called our amplitude. So in addition to being considered a vertical stretch, it is also an amplitude. Amplitude, the formal definition, is half the difference between the minimum and maximum values of the range. Only periodic functions with a bounded range have an amplitude, though. So sine and cosine both have that because they have that bounded range. Let's go back to the graph of sine and cosine together again. We graphed them, but we didn't actually talk about some of the similarities and differences. Did you jot down what you thought? One of the things that I notice is that these two graphs are identical, except they are a transformation of each other. They are both shifted either from one to the other, left or right, depending on, by one box, which here represents pi over 2. So there's a transformation of pi over 2, either to the left or to the right, depending on if you're going from sine or cosine. And that ties into our cofunctions as well. Now, back to this graph for a second. This 3 on the outside created a vertical stretch. I wonder what would happen if instead of being on the outside, right here, it was placed in with the x, as like a sine of 3x. I'm sure that that graph will look different, but the question is, how will it look different? Okay, this is where I'm going to stop because I'm going to pick up with this rest of this lesson on Friday. But before you go, make a little note of what you predict would happen with y equals sine of 3x.